Welcome to StudyOrgo's edition of the explanation of an E2 reaction mechanism. In this reaction, a haloalkane with a good leaving group, such as bromine, is reacted with a strong base, which is also a strong nucleophile. In this case, sodium methoxide is used. To eliminate the alpha carbon proton of the reactant to form a double bond. The alpha carbon can be found next to the carbon with the leaving group. It will have a proton bonded to the carbon. For the reaction to proceed, the strong base will break the carbon-hydrogen bond, and this will lead to the breakage of the carbon-bromine bond to form the final product, which is a carbon-carbon double bond. Let's take a look at the reaction mechanism. An E2 reaction mechanism is said to be concerted, in that there is only one step to this reaction. The strong base is going to attack the alpha carbon proton. The electrons from the carbon-hydrogen bond will then flow between the two carbons to make a carbon-carbon double bond, and at the same time break the carbon-bromine bond. In this reaction, a transition state is formed. The transition state is important for predicting the final product. In order for an E2 reaction mechanism to proceed, it has to align the leaving group as well as the alpha carbon proton in the anti-periplanar geometry. The result of the reaction will be a weak base, in this case methanol, and the final product, which is the alkene. We at StudyOrgo like to give you the tips and tricks to help you successfully predict the reaction mechanism for the individual problems you'll experience on the exam. However, the large number of variables for an E2 mechanism makes this difficult to explain. So we have efficiently organized the variables into a convenient table to help you study. By clicking on the Additional Materials tab and then the Study Charts tab, you will find the E1 and E2 comparison chart. On the top of the chart, you will see the stratification of the reactions, in this case E1 and E2, as well as SN1 and SN2. And on the left, the list of the variables that you'll have to consider. Let's take a look at the first variable. Kinetics refers to the rate order of the reaction. In this case, E2 stands for second order, meaning that both the concentration of the reactants as well as the concentration of the strong base will determine the rate of the reaction. That is because the mechanism is concerted, meaning that formation of the transition state depends on the nucleophile attacking as well as the reactant concentration. For the mechanism, remember that an E2 reaction mechanism is concerted, meaning that concentration of the strong base and attack on the alpha carbon proton is as important as the concentration of the reactant with the strong leaving group. The solvents for an E2 reaction need to be polar aprotic, meaning that the solvent has no ionizable protons to react with. If our solvent was water, which has two ionizable protons on it, our strong base nucleophile would simply attack the water molecule and remove the proton in an acid-base reaction. This would decrease the concentration of the base, and as we noted in the kinetics section, this would decrease the rate of the reaction. The substrates that react fastest with an E2 reaction are tertiary and secondary centers that have the leaving group, but they can also react with primary carbons as well. Remember that because the strong base will attack the alpha carbon proton and it is not directly attacking the carbon center with the leaving group, like in the SN2 reaction, the accessibility to the proton on the alpha carbon is usually pretty easy. Good leaving groups are required for the E2 reaction. Tosyl groups, as well as halogens, are always good choices. A strong nucleophile is always required for an E2 reaction mechanism. The strong nucleophile also has to be a strong base. That is because in an E2 reaction, the alpha carbon proton removal is essentially an acid-base reaction, and a strong base is required to break the carbon-hydrogen bond. Remember that the stereochemistry of the reactant has to orientate the alpha carbon proton and the leaving group in an anti-periplanar geometry. Make sure to rotate the substituent in 3 dimensions accurately to predict the right alkene product. To do this, be sure to draw the Newman projection. Many molecules have more than one alpha carbon next to a leaving group that you could react with via an E2 elimination. So which one do you choose? Well, in our example of methoxide being our strong base, the E2 elimination will favor the Zaitsev product. This means that the double bond will be formed between the carbons with the most substitution, or said differently, the more substituted alkene product will be formed. This is regioselectivity, and for E2 mechanisms, it depends on the bulkiness of the base. If it is a small and non-bulky base, like methoxide, the Zaitsev product will be formed. However, if terp-butoxide is chosen, which is a very bulky base, then the less substituted product, which is called the Hofmann product, will be observed. Rearrangements are never observed for an E2 mechanism because the mechanism is concerted. There is no opportunity for a rearrangement to occur. And finally, increasing the temperature is always an efficient way to increase the energy of the reactants to overcome the transition state and the intermediates to get to the final product. That concludes our explanation of the E2 mechanism. We thank you for watching.